The rest of calculus studies is integrals, right? So we've done limits, derivatives, the rest is integrals, okay? All an integral is calculating the area under the curve of a function, okay? So I give you some function, it doesn't matter what it is at this point. What we're going to study is how to calculate this area because it's not a standard shape like a rectangle or a trapezoid or a circle, right? That's how you know area. Okay, the study of calculus brings it into irregular shapes. Okay. We'll also study a little bit of volume, okay, where we create three-dimensional shapes based on these. And that's it. That's our semester, our quarter, and then we're done with calc. Woo! Right? So what we're going to focus on first is how do we estimate, Jason?
So what is chapter 5? So chapter 4 is derivatives.
Chapter 5 is calculating integrals. Chapter 6 is applying integrals. That's the rest of our year, basically. Okay. So, because we don't know how to calculate this quite yet, exactly, we need to estimate, right? So, estimating is a good tool if you have the need for it. So, just give you some function. An integral is going to give you an exact answer. Okay. We have to learn how to calculate those. We can estimate the area under this curve from A to B using rectangles or trapezoids. Those are our main shapes that we use. Okay. If I estimate it with three rectangles. Okay, so let's say I draw three rectangles under that curve. The left top point of each of those rectangles hits the curve, right? That's called a left Riemann sum, okay, because the left corner of each rectangle is on the graph. So this is called a left Riemann sum. Okay. Good there? Vocab word. How many rectangles are there? Three. So this is three what we call sub-intervals. Okay. So we have three sub-intervals of that one interval A to B. Okay. So if I calculate the area of all these rectangles, I get an approximation of the area under that curve, right? And you can calculate rectangle area. I'll go through a couple examples. Don't worry. Right? This is just the vocab. All right. So that's a left Riemann sum. A right Riemann sum. What do you think happens?
Oh, right corner.
We start from the right side, the right corner. These are our rectangles now. Okay. So start from the right, and the right corner intersects. That's called a right Riemann sum.
Is there one that should be used more often than the other, or just depend on the graph?
Nope. Just what you're asked to do basically at this point. In reality, so he brings up a good point. Which one would we want to use? Why?
Because it's under it.
So you prefer an underestimate?
I think, well, it depends on application and context.
Right? A left Riemann sum would be an underestimate, correct? Because we have these three pieces that are not accounted for.
So we want to do the right?
Okay. Well, the right Riemann sum would be an overestimate because we're above it. Okay, that's one way to deal with it, is to take the average. Okay.
So, on that note, if you take the average of a left Riemann sum and a right Riemann sum, would that give you? Why not?
It's not exact because this is a
So in a real
exponential
world,
curve.
in a real world,
It's going to be close. Just like if we put trapezoids here, it's going to be close, but it's never exact, and that's why we move into integrals. So you're seeing some inexact answers here, right? If you need an exact answer, you need to go to an integral. That's where we're headed. But this gives you an idea of what we're looking at, okay? So we're going to study left and right Riemann sums and how to calculate those today, right? So let's start with our old standby.
X squared.
Okay. So it might say approximate the area under the curve f of x equals x squared with 4 subintervals. On, we'll make it easy on this one. 0 to 4. Okay. So that's an example of something you're going to calculate.
Mr. Arthur, if it said 2 subintervals on 0 to 4, would you only have 2 rectangles? One 0 to 2 and one to 2 to 4?
Exactly. Yeah. Do you want me to draw the picture? So there are ways to this. Sometimes you're given a picture, sometimes you're given a function, sometimes you're given a table. Let's start with the picture. Yeah, I know. Don't worry, we'll talk about airplanes here in a bit. Okay, so we have our 4 subintervals, right?
Yep.
If we have a left Riemann sum, we have to start on the left side. How tall is this rectangle?
Not very.
It's actually 0. Because this point is 0, 0, correct? So that rectangle doesn't exist. Yay, right? No calculation there. All right. What point is this on the graph?
1.
Yeah, 1, 1, right?
Oh, yeah.
So how tall and how wide are my rectangle?
1.
Yeah, so the area of this rectangle is 1 times 1, right? Because it's 1 wide and 1 tall. Wait. What about that point? 2, 4, because 2, plug 2 in. 2 squared is 4, right? How big is that rectangle? No. That's the most common mistake people make. How wide is it?
Well, 1.
It's 1 unit wide,
But 4 units.
but 4 tall.
So 4.
Yeah, so be careful there. 1 times 4. So that's 4 units squared. And then the other one, yeah, 3, 9. So the area is, yeah, 9 squared units. Let me pick a color here. 1 times 9, which is 9. Okay. So what is the sum of the area?
14 each.
1 plus 4. There's your answer. Left Riemann sum. Okay.
So would you just put unit squared?
Yeah, if you need to.
So you don't have to.
In a context, in like an airplane problem, they probably ask you for units, and it would be units you'd state. The actual answer is 64 over 3, the perfect area under this curve, which is 21 and a third. Okay, so there's we're a little under, right? So, and I'll teach you how to do that, no big deal. Okay. All right, so that's with the graph or the function, right? If you have the function, all you have to do is plug the values in and get the heights of your rectangle. Okay. These are actually easiest when you have a table. And okay. Sometimes you're actually given this table. Okay.
Why were you including 4?
You're going to be given, so some of the problems will give you
More information?
0 to 4 is your interval, and you're asked to calculate it on the left Riemann sum on 4 subintervals, right? Then in this case, you don't need that, right? But to satisfy the interval, it shows you all the data. And if you're asked for a right Riemann sum, you need that data. So, all right. So our rectangles are basically are given to us here, right? So from 0 to 1, we have how many subintervals? 4?
Yeah.
Right? Okay. How wide is our first rectangle? 1 unit. And how tall is it? 0. Left rectangle, see it? Okay, so 0 times 1. And then our second rectangle is 1 wide and 1 tall. See how the tables are easier?
Too tall. They're too wide.
Yeah, so, and then you finish it off. You got 1 tall and 4 wide. Or sorry, 1 wide and 4 tall, right? And then you have your last one, which is 1 by 9. Okay, and you can see that the left point of the rectangles is the one we're using. It kind of all just graphically makes sense. So still 14. Okay. Yeah, and if you want to do a right Riemann sum, it'd be 16 by 1, 9 by 1, etc. Right?
So would that get us over then?
It'd be a big overestimate. Yeah. So, okay, so that's the 3 different things you might run up against using ask for a Riemann sum. A function, you might be given a graph, calculate, or you might be given a table to calculate. Okay. Just remember that left Riemann sum.
So with that, since you know the height and the base of the triangle can be used to calculate, to try to get a closer estimate, can you calculate the area of the triangle to try to get a closer?
Yeah. So tomorrow we will, since you're asking for it, tomorrow you could put a triangle here, right?
Right.
And make it closer estimate. That makes a trapezoid. Because you have a base and then a slanted sides. So this would be a trapezoid at that point, and I'm going to show you how to do that tomorrow. But yes, it's a closer estimate because some of this is filled in. Right. And we'll also talk next week about how to determine over and under estimates, how you justify that. Okay. Okay. Do you want to see a right Riemann sum?
Yes.
Yes, please.
trapezoids, is it still right to that corner?
A trapezoid uses both bases and the height. Well, tomorrow, let's wait till tomorrow.
Tomorrow.
Wait, Hunter. Oh, Hunter, don't do the wrong assignment again.
Double check, dude.
Into the
Just
glass.
eager to go forward.
Oh, we get that you're eager, man, but you gotta do the right one.
Yeah, I don't know how I'm supposed to write. Usually, at this point, lightning works right now.
Let's approximate the area under the curve of the data. We would also say maybe of g of x at that point. Okay. In the table using a right Riemann sum with 3 subintervals.
What's the boundary?
Sorry?
What's the boundaries? Like
1 to 7.
Given by the table.
wait, but so they don't always give you like to 0 to 6?
Don't have to. They probably would. Maybe. Or you could do that. Don't have to because it's there. Sometimes they'll give you a table and say 1 to 4 with 3 subintervals. So yeah, we should be specific.
Do they have to be uniform subintervals?
No, they do not. I've made this uniform, but they don't have to be.
How's that uniform? There are 3 of them.
Divide by 2, guys.
How many 1, 2, 3, 4, 5, there's 6 spaces.
So
We only
you
want 3
wide.
subintervals, so
Yeah, instead of
we're
having
gonna
a
go
bunch of
by,
ones, we're gonna have 2 wide ones.
we're gonna go by 2s now. Okay. So, it's a right Riemann sum, right? Start on the right. How wide is my rectangle?
50 by 2.
2 wide, 50 tall, right? And then we're at,
35 by 3.
how wide is that?
Or 2.
2.
That's really good.
30 by
2.
2. Okay, these are going to be no calculator problems, so don't use your calculators. Get the practice. If I'm on a free response, am I doing anything past this point?
No.
No, I'm not. If I'm on a multiple choice, I'm probably going to have to simplify it. In your homework, simplify everything. Practice that. I know it's arithmetic, but practice it.
So, are we gonna get practice to the point where we know when to stop, like for applications? Like, I feel like on all the tests we still go all the way.
A lot of you are, yeah. Some of you are not, but it just needs to be practiced. Okay, so there's a right Riemann sum with the different subinterval structure. Okay.
Figure out the height by adding the beginning and end area?
So that's
If you're,
overestimated?
what?
Like overestimated?
This function is increasing. So a right Riemann sum is an overestimate. Yeah.
This is probably like some wacky fun.
Right, so that's the extent of the calculations you're gonna have to do with these. Stuff you've always done, right? You're just putting it in a calculus context. Okay.
I have a question. Why did you go from 1 to 3 and then 3 to 5 again?
We were asked for 3 subintervals, but we have 6 numbers, right? Right, so we have to do every 2 numbers to get 3 subintervals. Yeah, so that makes each one of them 2 units wide. But do be careful, these are not always consistent. It's not always going to be 2, 2, and 2, or 1, 1, and 1. It could be 2 and 4, because your data in the table could be different. Okay. All right.
Kairos. 6 as in like you're only using
How we're going.
so you disregard or the 1, sorry.
Good? Okay. Let's put this in context a little bit.
Airplane?
Yes. The velocity, we'll do in kilometers per hour because the metric system's so cool, of a do you guys know what a super cub is?
Yeah.
Piper Super Cub.
Absolutely not.
Cub.
It's like a tube of something.
It's a pilot and a passenger. And it's like, I can barely get in.
Yeah, they're really small.
Yeah. I flew around in one last fall for in Alaska, and it's like,
Yeah.
it's really cool though. Yeah, it was a float plane too. Okay, the velocity of a Piper Super Cub aircraft traveling due west is recorded every minute Hi. 10 every minute for 10 minutes. You want to do a left or a right? Let's do a left. Okay. Use a left Riemann sum to estimate the distance traveled lots of work here. Whew. How many subintervals do you want to do?
5.
Somebody said 10.
Why? Hey, Garrett.
Garrett, good job.
Woo!
So you get to choose how many?
Yeah.
No.
They
I just
tell
let
you.
you choose because I didn't put it on there. The example in the book is using something called Simpsons Rule, which we don't have to learn. So I kind of augmented this too.
Does Simpsons Rule have to be with plane or math?
It's just another way to calculate it.
trying to figure out this.
So you're in an airplane buzzing along, and you're like, oh, I'm going to do some calculus. It turns out that I was going 80 kilometers an hour in the first minute, at the first minute. At the second minute, I was going 100, and then 128, third, 144 at the fourth. Okay, is there any data in here that indicates distance traveled?
No.
No, there's not. But we're given velocity, right?
Right.
You remember this relationship?
Can't we do like the...
We're hanging out in velocity. How do we get to the distance traveled, which is a position change? Antiderivative. Right, so we are calculating an antiderivative here with numerically. Okay, so keep in mind that the antiderivative of a rate function, of velocity in this case, is going to give us a position change, or distance traveled in this context. Okay, so that is a big concept. Okay, there's always a free response on the AP exam that looks like this. Maybe a table, it may be a function, but there's always a problem like this. Okay, Montaigne.
Wouldn't a more accurate way to estimate this is find the average of those, and then realize that 10 minutes is a sixth of an hour? So like, if you're going, your average was 100 kilometers per hour in the 10 minutes, then you can just divide that by 6 and you have that, right? Because you find your average speed, and then you do how long you were traveling for, that gives you your distance.
In kilometers.
Yes.
That would be one way to do it.
Isn't that what we're doing, just we're doing a harder version of it?
Well, if you don't have a calculator, though.
You don't need a calculator for that.
Close. Okay.
It's just long division.
Well, now it's
So Montaigne brought up an interesting point, though.
Yeah.
We're in kilometers per hour here, and we're in minutes here.
Well, 10 minutes is just
Okay.
a sixth
So
of an hour.
this is, how much of an hour is that?
1/10.
1/60th. Okay, so our interval width has to be a 60th of an hour. Right? Okay, so left Riemann sum, what's the first width? 1/60th. And 0 tall, right?
Why are we doing this? It seems so much harder than if you were to just calculate the average.
This is what we're asked to do. How wide? 1/60th.
Yeah.
Times 8.
What is that, 2?
Right?
It's not 2. No.
How wide is this?
1/60.
Times.
Oh, why does that have to be so much? Why do we have to see?
Okay, do you notice this is the same every time?
Yeah.
Yeah, so
Okay.
take your y and
Can
multiply
I
by 1.
factor that out?
Yes.
Yeah, you can. Well, at the end,
Here's an easier way to do these. If the subintervals are all the same, I can put that out front, and all I have to do is add all these up. Because that's what it's going to do, 0, 80, 100, right? $128. Which number do I need to stop at?
136.
Not 136, 120. Because it's a left sum, right? So I have to. Now feel free to write out this version up top. It's just a lot easier to do the bottom one. Okay, so same thing.
Question.
Okay.
If we brain farted and didn't know how to do left Riemann sum, but we realized that you can calculate the average without it, and we get the right answer, and we get a point for the right answer, but not for using the correct solution.
You get, so this problem is gonna be worth 2 points.
Okay.
One for this
Okay.
and one for the answer.
So you could still
So
get.
if you write this out, this is 2 points right here if you just leave it, because it's a numeric answer. Or you can do some other method and get an answer. If it's right, and the method is a legitimate method, you'll probably get the answer point. I don't know if they'll give you the Riemann sum point. I would just follow directions. Okay. All right. So does anybody have that number?
Working on it.
Okay. Divided by 60.
Yeah. It is hard work.
17.46.
Units?
Kilometers per hour.
Oh. It's a position change.
Kilometers.
Thank you. All right.
Wow. Just got yelled at.
I think he's upset.
I am a little bit.
Why?
Because I totally had a great solution method that works.
I have to think about it, Montaigne.
Well, it asked you to use Riemann Sum.
So you got it.
It specifically asked you
Okay.
that, so.
Questions?
No.
Okay, left and right Riemann sums, and then the antiderivative or integral of a rate problem is a position change. That's one thing that I wanted to introduce you today. Okay. There is a worksheet posted on Google Classroom. Do you want me to write the problem numbers up here?
Yeah.
Okay. It's for today and tomorrow, but this work is, we're going to score tomorrow. So 1A and B, 2A and B, and 6A and B. And then 5.1 from the book, 1, 7A, 11, and 19. Okay.
Is that worksheet the thing you're supposed to do in break?
Nope.
And are these both due tomorrow?
That's a good question.
Who didn't get what we were supposed to do on break? Okay. I'll hand that to you.
I didn't get it. Yeah.
Let me shut this down.
I just with me on it.